Good morning. You guys hear me? Chapman.
Morning.
All right. Charlie, can you hear me? Uh-oh. Well, at least I know Chapman can hear me.
He says he can hear us. But he can't for some
Oh,
reason.
great.
He
I
can.
see the chat. Thank you.
Oh, I think there's a button that says allow to talk next to people. So maybe they're not allowed to talk until I click that. Let me click that for him.
I do not see that. All right. Participants.
Okay. Oh, attendees versus participants. Yeah. So now I think Charlie is an
Can you hear me
attendee.
now?
Yeah. Okay.
Yeah, that was it. I was like, my mic is showing just fine. I did the microphone test. Yeah, okay.
Well, when you're on a university Zoom call, it's all locked down because we don't want anyone to be disruptive during lecture.
We wouldn't want to, and yeah, I was gonna joke. So we wouldn't want to share information at universities.
Yeah, so if we want anyone else to talk during this, we'll need to add them as we need to allow them to talk. So
All right.
yeah.
Well, I would propose that probably to avoid having to scroll down through a list of a couple dozen attendees and unclick someone to unmute for a question, we ask people to type comments into the or questions into the chat and use the raise hand feature. So I see the attendee list is rapidly rising as it tends to right on time. So we'll give folks a few more minutes to sign in. Thanks again for speaking, Charlie, and for being flexible with the dates and timing as well. The tumult in the external world worked its way down to scheduling, even for webinars.
No problem.
So at some point, are you able to share your screen as well, Charlie? Have we enabled that properly?
Yeah, we should try to make sure that works. Yeah. I don't see a button allowing me to do that right now in my controls.
Chapman, do you have the ability to add that to him?
Yeah, let me look.
Oh, here, I'm going to change his role to a panelist. That should do it.
Okay.
Change role to panelist. Do you have to approve that, Charlie? There you go. Can you share now?
And I think let's go for it.
All right. Well, we are 2 minutes after the hour, and we have the slides being shared. So with that, let me officially welcome everyone to the US Map webinar for this month. It's our pleasure to be hosting this virtually on behalf of the US Map team from the University of Washington Clean Energy Institute. It's our distinct pleasure to have Charlie Hasselbrink today. Charlie is currently the Chief Technology Officer at Calyx. I mean, you probably already know him already. He previously led global quality, reliability, R&D, and performance R&D during his 9 years at SunPower. He's been an advocate and champion for PV reliability. He's been a plenary speaker at the IEEE PV Specialist Conference, was an area chair for reliability at PVSC 42. He's been VP of reliability at Mainspring and a VP at front-end technology at Sila Nanotechnologies. He's previously held roles as a tenure track faculty member in mechanical engineering at University of Michigan. Go Buckeyes. Oh, sorry, I grew up in the wrong state for you. Okay, and he got a PhD in Stanford and a bachelor's in mechanical engineering from University of Houston. Go Florida? I don't know.
Yeah,
Sorry.
right. I know. I was waiting for that.
Rough time for you guys. Sorry about that.
Rough month.
So, right. I think you're probably aware, Kalex is working on 4-terminal perovskite tandems and for use with silicon panels. And I won't do any more about their technology, but I'll save the time for him to give the talk today. So Charlie, please take it away.
All right. Well, thank you, Professor Ginger and Chapman, for the technical support and getting this going. And thank you, everybody else, for attending. I'll try to make sure this is worth your time. Yeah, so I'll just give a short update on, the subject of this one is really just going to focus on an update on what Kalex is up to. We'll talk about some of the challenges that have come up. And as we start to get into the transition from lab to fab, now the next thing is to go from fab to market, and those difficulties are still there. And so new things that come up that are motivated by the differences between perovskites and silicon, are sort of front and center right now. So we'll talk about what those issues are. Don't necessarily always have solutions. I know there's lots of teams already working on them. Some of you may be in attendance, and I in a way, I wanted to make sure that there was plenty of motivation for your work that you're doing on those committees and standards. So thank you so much for the work you're doing. And then with that, we'll just get started. I'll just start with a little update here, or just the kind of the marketing department's view of Kalex. What do we do? Let's see, make sure to get a laser pointer going here. So you can start with any crystalline silicon module. As they work, of course, they have standard clear glass. You've got an encapsulant layer on top of that. If you take an active glass layer and put that on top, it's totally independent, electrically, mechanically, chemically isolated from the silicon by the layer of encapsulant between. You create a 4-terminal tandem, of course. And so our tagline is to amplify solar by 30%. And built for scale and for any use case. Those are two really key things in our strategy. Is any silicon manufacturer can go ahead and amplify the power of their solar panel. All you do is consign glass to us. We will put our perovskite thin film layers on the glass. We will design the product so that voltage matches to your product. And then there's really no change. You just you take 4 terminals, put them into your junction boxes, and tie the terminals together, so they will be voltage matched. And then there's really no difference at the system level, except for the fact that there's higher amps coming out of each string. The voltages will remain the same. So there's no additional complexity on the installation side. Of course, that's an issue when you've got maximum voltage limits, which often limit how you put in your how much BOS you need to have to be able to handle that, and what voltage limits how many strings you can put together, and how much voltage you can generate. So, it's drop-in replacement. We do have a really nice list of climate investors on our cap table. We are scaling the largest fab of its kind right now. It's aiming for 100 megawatts. We have 50 megawatts capacity installed. We don't always run it at 50 megawatts capacity or speed for right now. We, of course, are working out bugs in the manufacturing process and in the the production flow and things like that. So, but it's an exciting time for sure. We have lots of interest from partners that we've talked to, customers that we've talked to. a huge amount of pipeline of interest, more than we can possibly produce in the next year for sure. So for everyone who's working in perovskites, there's definitely a lot of interest, obviously. But the demand really is there for something that can add more power, more energy, and a lower cost of energy. So, just diving the next level technically down, so you can see where the breakpoint is between the marketing slides and my slides. The structure of this is basically we have these long skinny cells that we scribe as of course, to keep the sheet resistance losses down in the transparent conducting oxides. We string a panel, for example, we might have maybe these cells actually would roughly be about 5 millimeters wide and about 2 meters long. Those 5 millimeter by 2 meter long cells, of course, if it's about a meter wide panel, 1 by 2 meter panel, then you've got roughly 200 of them. They generate roughly 1.2 volts a piece, and they generate so about 240 volts natively. And we string them this way, divide them by 4, so with plus and minus terminals strung something like this. And now, of course, we have 60 volts here, and 60 volts is typical number for silicon panels. Of course, it's never exactly 60. In fact, we just did a delivery of some panels at 57 volts. That was the requested voltage. So, of course, we had to adjust the thickness of these cells a little bit in order to fit them in. And of course, we've got to go ahead and play games with the matching of these strings here. Ideally, you match those so that these tabs that we put over the product line up with the spaces between the cells for minimum shading. But as it is, these tabs are only a few millimeters wide, so you don't lose too much current through them that way. The top layer, of course, is converting the visible portion of the spectrum. We have a 1.56 eV band gap on our product, so we absorb up to about 750. The remainder is picked up by the silicon out to the end of silicon's band gap. And then, of course, that converts about 9%, so we get about 8.5 to 9 out of the bottom cell. We are aiming for 17.5 out of this cell. Right now, we're not there yet. I'll show some data about that, show where we're at. But we are working through the defect Pareto that's limiting our success there. So where are we? We have been scaling our process, and you can see our little glimpses of our production facility here in the background. It's about a 38,000 square foot facility that we have here in Baldwin Park. We have been producing panels since September. We have been also sending active glass to Asia, to a partner in Asia. So you can see what was going on their line here. They were tabbing things differently from how we were for a demo unit. Our reliability is probably the most important thing that we're focused on. We have what was called a Rev 5.2 chemistry. We put that in the field, and we've done Arrhenius testing on that. And then we have another Rev 7 that it says about 11.9 year. If you test it at ISOS L2 and you create an Arrhenius plot out of that, and you ask the question of where will we be at our normal module operating temperature, which we've calculated as 42 degrees, we would see that we have a significant improvement of Rev 7 over Rev 5.2. That's drawn these lines. And then you might ask the question, okay, but what do you really do in the field? The actual field result that we've gotten with the same Rev 5.2 chemistry was about 1.3 years T80. And if you draw that line back over here to this plot, you'd say, well, why were you hotter than your normal module operating temperature? And the reason is really clear. I mean, we were testing these at UC Merced with Sarah Kurtz, and those panels were running hotter in a hotter environment. So it's not terribly surprising. But the other thing is that the very hot days, this is an Arrhenius plot, and it's got a pretty high activation energy. So that means that those hot days where you're actually exceeding 48.5 and exceeding NMOT, where the wind's not blowing too fast, those hot days really matter. So they'll really start shortening the life. So I'm not claiming that we have an 11.9 year product yet. I would claim that we have, dramatically improve the product, but we still need to do the outdoor testing in order for that to happen. If this were to hold true, if we were still to hold it to 48.5, if I draw that line up here, it'll be somewhere around 3 years with our Rev 7 chemistry. We have other chemistries that are under development right now as well. We're also, actively looking at as people in the academic world start to publish new chemistries and new things like that. We are happy to license chemistries that enable this revolution with perovskites that we expect to happen in the next year or two. All right, so here's some of our data here. We've got 1.56 EV band gap perovskites, so these are not tailored to capturing records. The main thing that we're trying to do is make a great tandem, so not necessarily the perovskite itself. And when we build these in their factory, we build them in multiple formats. We've noticed a lot of people report results in different formats. They might report a hero cell that's less than a square centimeter. We try not to do that. We try to be really crystal clear about what we're talking about. And the other part is, hey, was that made in the lab or was that made in the fab? And hey, is that the same chemistry as you're getting for your durability numbers that you're reporting? We're seeing a lot of what I think we're seeing in the literature is we're seeing a lot of gamesmanship with that. We don't like it. We try to caution our investors about that. And we try to be as crystal clear as we can be about exactly what we're talking about when we show our results. So these are what we call PMs. These are production mini modules. So that's, we're seeing there's a 3x4. We can do up to 60 such devices on a single 1x2 panel. The numbers, the XXX is a number. So a PM 259 means a 200, oops, there's a typo there, 259 centimeters squared. PM 110 would be 110 square centimeter active area device, for example, with tabs on it. Number of cells may vary. You can kind of guess from the voltage. The substrate size may be 6 to 8 inches typically. And the reason for that is because we're able to take these production mini modules, we're able to break the glass, scribe it, break it, and send it into the fab. And then we can do splits between the lab and the fab. So we might produce up to a certain step in the fab and then say, okay, well, we're not sure this step is achieving in the fab what it should be able to do. So we go ahead and take that cell, cut it up, send it over to the lab, and then we can compare the two processes. An important thing of what we're doing at Calyx as well, a part of our strategy, is that yes, while we do have spin coaters in the lab, we have an analog in the lab of every single process step that we're doing at scale. And in fact, in some cases, in many cases actually, so with our lasers, for instance, our production laser is also the manufacturer of our lab laser. The manufacturer of our perovskite deposition tool is also the same company that makes our small lab version of the same tool. Uses the same physics, made by the same vendor. The advantage of that is, of course, that as you do this translation from lab to fab, you can do these split experiments where you're breaking up the module into pieces and sending it through, okay, here's the small version of the tool versus the large version of the tool. Why are we getting a different result? Zero in on the physics and the chemistry that might be different between those two processes and hopefully quickly resolve problems that you're having in that translation. So that is one of the first big challenges is going to scale. So those uniformity studies as well are also super important. So we do see, of course, uniformity variations. For instance, you might see axial or X, we call it, this is the X direction in the long direction of the panel. And this is the Y direction here internally at Calyx, just our internal shorthand. And so you may see X and Y direction variations. And then, okay, question, why is that happening? How much impact is that happening on the PCE overall? So we're able to do those studies. If we take a device, one of these devices that's cut from something that went all the way through all of our production factory equipment, we're hitting about 12% right now. We've hit over 14%. There's one step that we know has got a little problem with it. We're putting in better equipment, new equipment right now. When we use the lab equipment, we do the split, as I was talking about, we're up to 14% on a given spot there. And in our lab, our lab devices, we've gotten up to over 21% devices and really small scale devices. We know that it's limited, of course, by uniformity. And then many, many point defects. We can see plenty of those. We've got lots of work to do in eliminating those point defects. So there's a pretty clear path on at least how to get up to our target of 17.5% on the perovskite side of things, which would lead at least a 26-27% panel. Our large scale panels, so we call these F, so that's full size modules, mask 1, mask 2. Mask 1 is actually 200 or it's more than that, so roughly, sorry, it's less than that. It's about 180 cells running across the width here. So that generates roughly about 200 volts. And then so you see a tab here and you see a tab on the far end. So that's a high voltage panel. That's not something that most of our customers want to integrate with their silicon cell because they don't have 200 volt silicon panels. We have a multi-lane version of this. We call it F1M3. It has the multiple tabs like I showed on one of the first slides early on. We also have one called the F1M2, and we'll be clear about that as well. The F1M2 is 1.25 square meters. When we had some non-uniformity issues that were more serious on the edges and at the start of this perovskite deposition and the end of the perovskite deposition, we were using the F1M2 as a proxy. On that, we've gotten very close, teasingly close to 10%. I think that's actually 9.8, not 9.6 at this point. So on a scale that is, roughly 1 by 2 meters. All right, so hopefully that describes enough about the product and how we're making it. I'll switch over to the technical and market challenges we're seeing in the world on quality number one. So the process scaling, we actually that's always a technical problem. I already talked about how we're addressing that, so I won't go over that in more details. Uniformity over large areas and point defects are really the two main categories that we see as ways to attack this. The uniformity actually is not that bad of a problem. Most of the things that we've seen are very addressable. Depending on the choice of tools and choice of methods that you've used. We do have this one process step that I mentioned was problematic, and we realized, we need to go a different direction. So that's given us a little bit of a delay, but other than that, so far so good. Unfortunately, I realized that right before this webinar, I hadn't put in a picture of one of our data points showing the uniformity of our perovskite. That one actually has gone quite well. Our engineer who's been in charge of that has done a really nice job. The point defects, like I said, we see plenty of pinholes. So lots of good opportunity there to go after the root causes of those pinholes. So we're building a defect Pareto library and looking after those. Some of them are point defects. Sometimes they look like lines and streaks and things like that. Wetting issues, things like that. And so those are sort of the Pareto that we're working our way through. On the technical side also, the industry, chemical process industry upstream of us doesn't have, in some cases they sell perovskite grade chemistry, of course. Knowing exactly what those specs are and what purification steps are needed is something that I think the industry itself is going to have to learn, and it may learn the hard way. That's a possibility. But we are doing our best to try to stay on top of what those certificates of assurance need to look like and how we can verify those with suppliers. We do, of course, use our lab as a qualification laboratory for our product before we go out trying to make it. Another quality assurance issue is the metastable behavior of perovskites, of course, and I think most of you have seen some evidence of that in your research. Or otherwise, and that metastable behavior is certainly an interesting one. That creates some challenges in the testing. Just the simple fact of how to describe how many watts these panels have. Durability still a challenge, of course. Still have room to go on that. One of the I kind of categorize these as by stresses, but the physical mechanisms are manifold for a given set of stresses. So light and heat and oxygen, well known to be one of the bigger issues for perovskites. There are at least a couple of different mechanisms possible with light and heat and oxygen. And then reverse bias durability. That reverse bias can be a real, a reality in the field, especially in rooftop applications. So the value proposition for taking a silicon panel and adding 30% more efficiency out of it is certainly strongest in the rooftop market, constrained rooftop market. That said, reverse bias is not a major issue typically in power plants. It can be, depending on if you've got location of power towers and things like that nearby. But generally, it's less significant in power plants. But of course, in high soiling environments, that can be a problem as well. High temp, that's actually a reason, by the way, the reverse bias sensitivity is a reason why we decided not to pursue 2-terminal tandems. 4-terminal tandems, when they're voltage matched, yes, the individual strings may be biased, but because you have a string of silicon cells in parallel with a string of perovskite, and the two have completely different form factors. One is really long and thin, and the other one is short and square and compact. So as a result of that, the likelihood that both are reverse biased at the same time or both are partially shaded at the same time is lessened. And so you've got an alternate path for current to go through as well. So depending on how we string these things, it's possible that we could actually ameliorate reverse bias issues for both the silicon and the perovskite. We have not gone and done detailed studies and tried to look at different shading scenarios yet and try to figure out exactly how to maximize that. I think that would be an interesting academic study, actually, if anyone were interested in doing it. The high temperature sensitivity. So we have seen this in others' data as well. And we certainly see it in ours that the perovskite material is sensitive to high temperatures on those very, very hot days. So that's an issue. And the higher that sensitivity is, the more difficult it is to do lifetime prediction. So that's definitely another issue. The next one is yield and performance. So figuring out how much yield we'll get out of these, with 2T, you'll have current mismatch, with 4T, you'll have voltage mismatch, how much impact that has in the production of the panel under normal circumstances even, is something that's, can be done by a simulation fairly accurately. So I think that's a good way to start doing those studies. I have seen papers talking about that. Looking at that as sort of power plant level, or at least a good size single individual strings, something that we're anxious to get done in the field. So we are actually producing, we're aiming to produce 100 kilowatts roughly of perovskite tandems this year, get them in the field and start monitoring their performance and their output, hopefully in comparison with the control of silicon only cells. And last but not least, temperature coefficients. Lots of interesting data out there about temperature coefficients for perovskites, and again, metastable behavior. So that's coming back and in the measurement of temperature coefficients. I think Tim Silverman said to me a year and a half ago, or a year and a bit ago, from Tim Silverman from NREL, hey, stop thinking of perovskites as a material and start thinking of it as as thin layers of chemicals that are constantly changing and moving around and finding new equilibria, something along those lines. And it just totally changed my thinking about this. And hand files certainly are not, we're not built with that type of thinking in mind. We're not going to have chemical mechanisms and things like that, changing states between different phases or something like that, for example. So all those are real complications. I will go in a little bit more detail now on these 3 areas that I'm prepared to talk about today, which are metastable behavior. Just going to go a little bit lightly into that one. That shows some examples of the light and heat and oxygen testing durability that we've been able to get, and some of the caveats about that the whole industry needs to watch out for. And then the last one will be this issue about temperature. So I'll dive into that one as well. Here's some data, some representative data for a 1 by 2 meter panel. Here's the PCE versus time. That's the orange, the black curve. And then the panel's temperature is measured by a thermocouple over time. And you can see the two kind of follow along each other. This is over a time of roughly 39 minutes. So it's quite a long time. You can see how long it takes for the panel to heat up, and you can see how long it takes for it to reach kind of a steady state PCE measurement. This is under continuous full-scale AAA light source illumination. We have invested in an Avalon tester that's capable of doing this. It has two light sources. In there, one is capable of doing continuous light soak at one sun. The other one does a flash, but it's a AAA plus. It's a better quality and better uniformity light source. That one is a flash source, and then this continuous AAA light source is been very useful in terms of doing experiments to diagnose what's going on with these. I will say this is sort of a poster boy. We don't always see this amount and this degree and this severity of temperature dependence and or light soak time period, metastability behavior, metastable behavior. So I did pick out a poster boy for this, but you can see they can have substantial variations. I mean, this is going from 8.8 to 9.8, as I mentioned earlier. And the issue with that is that, if we have a 45X and other economic incentives that are tied to, okay, well, how many watts did you produce? The difference in your incentive, financial incentive here between 9.8 and say 9.0 would be substantial. So that is certainly a big deal. It's 10% on your incentive. That's a problem. That's a real problem. So if we have to come up with if we do have these kinds of metastabilities, by the way, and even if this were 1/3 the magnitude, we know how thin the margins are in the solar industry. If it started at 9.6 and we could soak it for 39 minutes and get it to 9.8, it would probably be economically sensible for us to do that. So again, do we really want to spend all that time doing all of this light soaking? This seems a little bit seems a little bit it's a non-value added activity. Let me put it that way. So what's the sensible approach? I've thought about this only a little bit. I know there are standards committees that are pondering this as well and thinking hard about this. If we add the costs of a light soak, it's like, why would we add that non-value added activity? And then another question is, of course, what do you do about temperature? Not everybody has a continuous large scale tester. These days, it's actually economical to do it. The reason that the 25°C STC standard for testing solar panels was chosen is because it was convenient, and flash testers were ubiquitous, but continuous large-scale solars, like the LAX at NREL was a very expensive facility, and not all panel manufacturers. It doesn't make sense for every panel manufacturer to invest in something on that scale typically. Nowadays with LEDs, you can get a pretty darn good spectrum, and you can use a filtered reference cell in order to get to reasonably accurate, very accurate measurements using a continuous system. So the possibility is there to do it. It's just that, it takes a long time for things to settle in. That's a problem. But this does beg the question, if we are seeing, in fact, a positive temperature coefficient here, which we have seen in certain temperature regimes with our own product, actually, we do see that we have seen that in the past with some of our product and some of our lab samples, I should say. We see a positive temperature coefficient, and if that's the case, then you'd actually be incentivized to be reporting it at a higher temperature, right? And instead of a lower temperature. Another question that comes up, of course, is, hey, would we accept a lower than earned incentive, right? We should, if this is 9.8% panel and we're going to only get 90% of that is a possible way to go. It's not what we prefer, obviously. And our pan file will presumably report a very high yield because, in the first hour of operation, we're going to have a panel that's operating much higher, and that may add a lot of confusion downstream in the market. So that doesn't seem very, very nice for that reason. And Thirdly, you could correlate a short-term SOAP test and if these curves are repeatable, and you can demonstrate that those curves are repeatable and demonstrate correlation between this data point, let's say, and this data point here after a short amount of time. If you can show that correlation and maintain it constantly and do this test periodically on a representative sample or a random set of samples, and prove that to auditors, then maybe that's another way to go. That would give the benefit, of course, of more accurate measurement for incentive purposes without having to pay all the cost of these long light soaks. Okay. Another issue, of course, is that IEC tests aren't predictive for perovskites. I feel like I still see papers sometimes saying, here's how well we do in damp heat. People will take a perovskite, should expose it, bare perovskite or bare device to damp heat and show, hey, it's doing really great in damp heat, and not look at light and oxygen. It's okay to go ahead and show those data. That's fantastic. Want everyone to keep that up, of course, but our modules, I wouldn't argue that they last very long when they are exposed to humid environments. When we expose the bare perovskite devices with laser scribes on them to humid environments, they don't last so well. When we make them into glass mini modules with desiccant loaded PIB edge seals, they do great. So we've tested, I don't know why we stopped short of 3,000 hours just so we could say it, but you can see the result here. So we have basically no degradation, and that's because, of course, this is a package test. I know Joe Barry put that in a paper. It was in Joule, made that very comment. Joe Barry and other folks were talking about the roadmap for perovskites, and it was like, well, this is basically a package test. So I think this is well understood by folks within the community. So that's good news, though, that this is basically solved at the package level. This is nice insurance to have if you have a perovskite that it can handle the damp heat on its own as a bare perovskite. It certainly is nice insurance if you do have a PIB edge seal failure. Those certainly do occur. Delaminations, or hey, it wasn't quite laminated long enough or something like that, quality issues. But it's not really a must-have. So, and so my point here is that, yeah, even though damp heat, hey, we had basically no degradation after 2,700 hours, we certainly degraded in the field. And so that's clearly, and this is in a dry environment. So I'm actually kind of using the field data point to say, hey, that doesn't correlate with the damp heat testing in that case. Now, one test that we do find does seem to be reasonably predictive. The only remaining issue, of course, is what is the right temperature to use, and that can be complicated. Is the Arrhenius approach we use ISO SL2 currently. We're working towards LT2 with some cycling going on in there. These data basically are comparing two revisions of chemistry. Again, our older rev that we had been reporting previously was a Rev 5.2. That's what we did in this test here. This was a Rev 5.2 chemistry. That Rev 5.2 chemistry, again, if you just use the Arrhenius plot, if we extrapolated this to 25 degrees C, we would get something like 68 years. We don't think that's realistic. And so we were asking ourselves, what do we report to our investors? And yes, by the way, you're looking at this saying, is that really an Arrhenius plot? This is the T80, time to 80%. So if you have a linear degradation rate, of course, that's like 1 over the reaction rate or 1 over K, if that's what you're used to seeing. So, and then the curve, of course, inverts its direction. So you're used to seeing the curve going down. Investors like to see the curves going up and to the right. So I thought this was just cleaner and easier to describe it this way. But it's the same plot. So it's a logarithmic plot and then 1 over T on the bottom axis. The Rev 7 chemistry, it looks like a subtle difference here. At very high temperatures, they basically seem to be limited by a similar mechanism. There is, of course, the concern that these curves may not be perfectly linear. But if you take those and extrapolate them out, like I said, at 42C, which we calculate as our normal operating cell temperature, we get to our normal module operating temperature. Those are subtly different, but we would calculate, we get to an 11.9 year product. Now, if we back test and say, well, wait a minute, what about Rev 5.2? You got to 42 degrees C. If you say 42 degrees C is your normal temperature, should have lasted 3.9 years, only lasted 1.3. What's the difference? And almost certainly the difference is the temperature at the UC Merced test site. So the reality is, do I think we have do I think we have an 11.9 year product on the Rev 7? No, not yet. Again, I know I mentioned this earlier and I'm repeating myself, but it's somewhere, we think our Rev 7 is somewhere around 3 years. And like I said, we're testing other chemistries and we will do more outdoor testing and then the accelerated test. We also need to make sure we're covering the UV spectrum. Our light source in our lab that we're using is an LED light source, but we do check that we don't have excess degradation in UV as well. All right. One question I have, and I would like to challenge the perovskite world, both commercial and the academic world, think about is, can we agree to start reporting T80 lifetimes, at least at the NMOD or the NOCT and not at 25C? I saw a paper about a year ago reporting we had a T80 of 78 years at 25C, and that's just not a realistic temperature. So for the purposes of keeping the credibility of this industry and improving its credibility, I'd like to propose that as a gentle proposal. Then the question is, what is NOCT or NMOD? Well, if you look at silicon panels, you'll see there is some variance, but you'll see that they're very, very tightly grouped. I mean, they only range from 43 to 45, and they always say plus minus 2 degrees C. Some say plus minus 3. So these are all very, very, very similar. Average is 44.4. So that's great. That's basic thermodynamics, though. So basically, that NOCT is and NMOD are defined at a fixed amount of wind at a fixed temperature blowing over a panel while it's under, in the case of NMOD, for example, 800 watts per meter squared. And so basically you've already fixed how much energy is going into that panel and the thermal resistance there is between that panel and its ambient environment. By setting the wind speed, you're setting the convective heat transfer coefficient. And so just like a current source attached to a resistor, the voltage is going to be what it is at that point. So there's no surprise here that there's a very small variance if these tests are all done carefully. Really what this is a slight difference in how the tests were done. So if you look at one of these systems, so what's interesting is that we're working in the space of perovskite tandems over silicon. And with the perovskite tandem over silicon, we have two absorbers, and of course they absorb at different wavelength ranges. So a portion of the spectrum is absorbed by this thin film. There's a 400 micron nominal encapsulant between that and a silicon cell, and you have some more encapsulant and glass. This is a little bit different situation than if you have a single junction perovskite and there's no silicon cell underneath, and then that portion of the spectrum may not be getting absorbed. So the amount of current, the current represents how much power is being absorbed by the cell in this analogy, this circuit analogy. And the resistances are accounting for the conductive resistances in the encapsulant, glass, and in this convective boundary layer above. This is actually by far the dominant resistance in this type of an analysis. Excuse me. This is basically the one thermal, heat transfer mechanism that's not accounted for is any direct radiation of these hot materials to the radiative, sky, to the sky dome. But at these temperatures that we're talking about, that should not be dominant. You can take this circuit, by the way, and as you look at it, you can see I can just combine these two resistors, these three resistors, and these resistors, and generate a simpler looking circuit diagram that looks like this. And so here's the math. I won't go through it, but what you see very quickly is if you think that the temperature of the perovskite and the temperature of the silicon could be significantly different, then you have to argue that it must be, because there's a lower resistance on one side or the other. There is a lower resistance because somewhat lower resistance on the front surface of the panel because there's no encapsulant on this side, but here there's an encapsulant, glass, and convective. And from the thin film, there's only glass and convective. But this encapsulant's thermal resistance is not very significant compared to the convective boundary layer. Again, it's dominated by these resistors here on the end. So basically, these two resistors are about the same, and this resistor is actually quite small. And so as a result, you might expect these two temperatures not to be too different. We can go through the math in some of the papers, but I just provided these as reference for, what does those convective heat transfer resistances look like? It's something, and then that's 1 over this heat transfer coefficient is the resistance. So you can go through this analogy, draw the data from the literature. This is obviously a very old study. This has been well understood for a long time. Not surprising that the temperatures that you get between the cell and the air are linearly proportional to the irradiance that you have on the device. And from that, you can derive these coefficients that you need in order to do the analysis. Do a detailed balance of irradiance. Again, I won't go into it, but efficiency matters here. One thing I forgot to mention is that the current, when we say the power in, here, this Q1 and Q2, it's not just the irradiance, it's the irradiance net of the electricity that's generated. So any irradiance that's converted into, is either converted into heat or it's converted into electricity. We're going to subtract off the portion that's converted into electricity in order to get the net energy balance there. And so you can go through, section by section at different wavelength bands, look at how much is converted to various things. And when you do this math, just on the resistor network, you'll quickly find that the resistance 1, 2, this one here is a very small percent of the total resistance in the stack. The resistance on the front side is a little lower than, but we've actually assumed that the resistance on the front surface of the glass is lower than the resistance on the back, just because it's also aided by natural convection. It's also got impinging air on it rather than being on the lee side of the panel and in a recirculation region behind the panel typically. Excuse me. And as you find, with these assumptions in here, you would find that the traditional silicon panel, as we would guess, 44.4 degrees Celsius, that's actually, and have tuned the convective heat transfer coefficients so that they exactly match what we saw in those data sheets. The Calyx 1 tandem panel that we're aiming to release in early 2026, maybe a 26% panel. We'll have the 17.5% perovskite, 8.5% efficient silicon with these band gap. And in that calculation, when we do that, there's almost no difference between the silicon cell and the perovskite cell temperature. However, you notice the temperatures are lower, slightly lower than the silicon cell temperature, and that's because of the efficiency. If we're getting 26% efficiency instead of 22, that means 4% of the irradiance is converted to electricity, resulting in a lower temperature panel. Now, if you're making a perovskite single junction, you get, of course, a little different answer. You'll get that you can actually get quite a cool cell down at 35C with the same exact convective heat transfer coefficients and everything else in the model. And that's good for durability, actually. So that's some good news there. But of course, it just depends on your product, depends on your band gap. If you instead say, I'm going to increase the band gap of my, reduce the band gap in EV in order to capture a larger chunk of the spectrum and get to a better total overall efficiency, then this number will probably go up. So, basically, the standards and the PAN files, where I'm getting to is that the standards and the PAN files for all of these technologies, when you have tandems or if you have single junction and they have different band gaps, we've got to be careful with those and properly model that at different, when you have the sky spectrum varying on different days and things like that. So that will quickly get complicated. All right. So we've covered the issue of temperature and PAN files and those issues for PAN files and for energy prediction. I think I step back and look at, okay, what can different people contribute to the problem? National labs and standards boards certainly have the driver's seat when it comes to many of these issues that we're coming up on. Impartial research, setting the scientific basis for these things, is really where the national labs really did amazing work for silicon over the years in the last 2 decades. Also, another thing that's really important that national labs do is providing motivation and confidence to investors by tracking the industry. And I would argue that, and I made this argument recently at the PACT meeting, that and got very excited responses immediately from Laura and from Josh and from Tim, who immediately created a plot for me. We always plot the research cell efficiencies, and that's the chart that gets a lot of attention from folks. And of course, the perovskite story here is very exciting. There's another story that also is very exciting. This is a review from I think it was KAUST and Northwestern and other universities got together and wrote this review article here. Great paper. If you're looking at the stability and versus publication date, there certainly is a trend line here. I think this trend line would come in tighter if we did temperature adjustments for the test temperature, and we scrubbed it for the type of data. But I think a chart like this is super informative, because what it tells me is that we've gone in about 10 years, we've gone about a factor of 2 to the 10, or a factor of 1,000. We've gone 3 decades on durability in the last 10 years, which is super encouraging. If we can continue that, we will have certainly have met a huge milestone for perovskites, but a huge milestone for the world in getting us to an even significantly cheaper solar product, and just an incredible abundance of low emissions energy. So very excited about this, but would love to see PACT. I think Josh was able to, or sorry, Tim was actually able to quickly show a chart showing here's how people are doing on outdoor tests. Those outdoor tests are great, and they are ultimately what we need for sure. I would love to also see a chart like this for at least some kind of accelerated test that we feel is a good proxy for that. So settling on what those tests are that really do reveal the basic mechanisms that are limiting the life of perovskites in the field. Even if those aren't perfect, I feel like those would be still high value to plot and to show people, so that we can track the progress and understand the rate of that progress is being made. Because oftentimes it's not important. You don't have to get the test itself perfect. None of those accelerated tests are perfect anyways. So I would advocate for coming up with some kind of standardized type of test on this that we can track industry progress against. There's a huge economic opportunity. So this is where I'm going to close. I have one more slide after this just to summarize, but the economic opportunity for the U.S. is just enormous with perovskites, and that's what makes them exciting. I don't want this to be misunderstood, so I didn't put it in the slide, but I kind of see perovskites are to solar what fracking was to oil, and that may sound strange. I don't mean to say that the perovskites can cause earthquakes and other problems. What I mean to say is that perovskites are an opportunity for the United States to regain energy dominance, and that's what happened with fracking, and that's the opportunity here. So if you go to oil, you say, gee, Saudi Arabia had a huge advantage. They've got Canada has a huge advantage, but when you suddenly say, wait a minute, the technology shifts over to fracking, the U.S. has tremendous amounts of natural gas resources. And that has been obviously a huge energy boom in the United States, energy production boom. We're now an exporter instead of importer. I think the same thing could happen with perovskites. So, we've been, the fact is that the Western world is hopelessly behind in silicon panels. China dominated silicon solar cells and panel manufacturing by government subsidies of capital, cheap labor, copying Western equipment. That's what happened. But now they have these deep in-country supply chains, and they have a huge cost advantage at this point. So there's quite a bit of dominance there. It's real. Virtually everything needed in the supply chain for perovskites is made in the U.S., including glass. Glass is made in the U.S. Low iron glass, not so much, but glass refractory linings can be switched over to low iron refractory. But virtually everything needed for perovskites is already made in the U.S., which is already the home of a dominant CAD telluride thin film company that we all know. Solution deposited perovskites require basically a third of the capex and the labor of a silicon manufacturing facility. The labor costs are low. These are all huge advantages that China had before, but they simply don't apply so much in this type of industry. And the other piece is that solar is an economic boom for everyone. What happened in the green energy transition is that coal became uneconomic. That wasn't solar's fault, but as a result, coal miners did lose their jobs while there were subsidies for green energy, and that created political issues within for solar. At least it's perception. That doesn't need to be that way. There's no reason for that. Electrons don't wear political stripes. Energy is for everyone. Energy creates abundance for everyone. And this shift to solar and to perovskites, I think, is inevitable. The growing solar industry needs people to help make this happen, and retraining them is a win-win. If you think about an individual person trying to make an investment, I'm going to go learn how to either make solar panels or go install them. There's some effort on their part. There's some investment of their time and effort and maybe money on that. So we should be trying to find ways to do that. There are currently 18 Republican members of the House of Representatives who have significant solar manufacturing jobs in their districts. With perovskites, I think we could have 100, could have 200 of those districts, and there's no reason they need to be in one area or the other. So I think that's a big opportunity for perovskites to make a huge impact on the energy landscape and the energy economy for the United States. And in summary and conclusions, scientific progress on PCE and durability. We, amongst other companies as well, are making a lot of progress on scaling this and making this a reality. The next big focus, industry standards boards, national labs, supporting the standards improvements for market acceptance. Thank you for everybody who's on this call, who's doing work on those. For durability, quality, and yield. And then, of course, last but not least, it'd be good to see more policies that support growth of this in the U.S. So with that, I'll stop.
Thank you, Charlie. That was really fantastic. And I have moved, as you may have seen, from the parking lot of the elementary school to outside the lecture hall at the university. For those who have questions, we've got some time for Q&A. I see, some posting in already. So I'm not sure if you can see them or not, Charlie, but I'll read them out. First question I see coming up is, can you say how UV impacts durability of the perovskite solar cell? And also I note that if you happen to have asked a question earlier, I think my swap over from one locale to the other may have lost some of the thread for me. So please feel free to repost. So UV impacts on durability. Do you have any comments there you care to make?
Yeah, I think it depends on your stack. So if you're using organics in your stack, especially on the sun-facing side, that can be a problem for sure. And we have seen that. So that can be a big impact. We've seen a significant difference when we're using. So we've played with. Of course, we played with SAMs, monolayer SAMs on the sunny side, and we have seen durability issues when we use some of those. So I think it's very chemistry dependent, and that's a problem. So the standards, really need to go after that and say, make sure that we do have that UV exposure and that it's a representative enough exposure that'll reveal the problem if it exists.
Cool, thank you. Another one in there, what is the rationale for 2.2 millimeters in strengthened glass instead of tempered thicker glass?
I've talked to Tim Silverman about that actually just recently. Right now, there are quality issues with the 2 mm glass that seem to be a perfect storm of at least 3 different issues coming together at once. They're having a lot of breakage of 2.1. Even when we go to glass, it's a problem. We are happy to go to a 3.1 or 2.2. We would prefer to use 2.2 or 2.1 in our glass to make them lighter. Currently, I think there's a short-term problem where suppliers have been finding ways to cut costs, getting stuff out in the field only to find later that it breaks because of either edge seaming or tempering or other issues. That Tim Silverman is actually writing a paper right now to go, maybe he's released it already and I didn't see it yet. So I would recommend looking into that for a more detailed answer. We're agnostic to it, by the way. We're happy to move to either.
Okay. Well, I'll wait for a few more in the closing minutes. I'll ask one question, and I really liked your framing of the economic opportunity. Is it okay if we posted something to social media summarizing the webinar here, saying Charlie Hasselbrink at Kalux describes perovskites as the fracking of solar, opportunity to move from energy dependence to energy dominance, or would you prefer we don't?
I prefer on that one to hold that to yourselves for now. Let me get that run by our that was definitely my comment, not necessarily representing my company's views, but it's an analogy, and I just want to make sure it doesn't get into the
Yeah, exactly. That's why I asked. I think I might say that on the side myself, though, if it does. If I don't want to steal your I don't know if that's your personal analogy. I don't want to start stealing it.
Feel free to steal it and don't attribute it to me, but yeah, just feel free to steal it. Just blindly steal it. But yeah, I mean, it is kind of like that from the economic perspective that it presents for the United States to reestablish itself in this industry.
Yeah. All right, great. We have 2 more questions that popped in the meantime. One is, can you please talk about your unit economics? What is the cost of fabrication and how much it affects the price of final silicon plus perovskite modules? Are you able to comment any? Yeah,
I can comment on the total. So I won't comment on our costs. And even our pricing is there's still some discussion about our pricing. But the economics will work out that you'll actually have the cost per watt won't change on the panel level. So we're going to add watts. We're going to add some cost. The cost per watt will pencil out to be the same. The advantage is you've got much higher efficiency. So all of the other system costs now are being picked up by somebody else, right?
Yeah. Hence your comments on value proposition for areas and others. Yeah. How do you provide deposition process in large modules in fab? I think I got that right out of the Q&A.
Yeah, it's a solution deposition process. We try not to reveal details of how we're doing it. But we are essentially almost all of our layers are solution deposited.
Thank you. Yao has a comment here. He says, just a comment, he really likes your framing of a durability record chart. He thinks we should all brainstorm on what that would look like and how we could support it. I think that's a great proposal, especially with this community here. And that's, I think, one of the reasons for existence of USMAP.
And I'll just emphasize one more point, which is perfect is the enemy of the good. Let's not argue too much about what's perfect and what is the right way to do it with scientific perfection here. If you have to pick an average or representative activation energy or pseudo activation energy in order to say, here's how we temperature correct, that's fine. Just be very clear about it. But let's not get too precious about exactly what those are, and then people can talk about those other issues.
All right. Fantastic. Well, we are 1 minute past the hour, and so I will officially adjourn the seminar at this time. Thank you again so much on behalf of the whole USMAP consortium for delivering a great talk, and hope to see you all in person at the nearest opportunity. Thanks for joining, everyone. Have a great day.